Hear me? Yeah, I do. So, well, first, I wanted to thank also the organizers for letting me introduce our work here. My name is Simon Poblete. I'm part of the southeRNA group with Fabrizio Pucci, which is also in the audience. And I wanted to describe briefly what we could learn and what things we tried also in this specific puzzle. So, as in the group in general, I mean, as a brief description, what we use that for now, or since the latest challenges, we have been using AlphaFold as a starting point, then refine our structures with southeRNA or other eventually cross-reading models. And finally, there are further refinement with energy minimization in molecular dynamics. So since we used to work with molecular dynamics as well here, it was a kind of a straightforward way of trying to do a minimalistic approach to take a structure which is already known and put it into a water solvent. So in a few words, we did something slightly different to what most groups did, because we didn't start with the template that was provided, but we used the structure from AlphaFold, which in principle allowed us to introduce magnesium ions. Okay, so this opens another question, which I also wanted to present here, introduce, because we have to remember that AlphaFold is able to introduce ions, and it's also very interesting to know if it's doing the right work on that. Okay, so I'm going to come back to that at the end. After doing this procedure, we selected the most different structures. In this case, two models that are slightly different, but they could have some specific structural differences in a few nucleotides that are at the beginning of the dangling in a non-structure domain. And also, this is part of the protocol. We also, whenever we take a model from AlphaFold, or whenever it comes, we check for possible entanglements and correct them as needed. But in this case, was not the case. Okay, but anyway, I just tell you that it's part of standard check, or sanity check for every structure generated from a web server. So to continue with this, once we have the structures which are pretty similar, okay, to the target structure that we were provided, we perform restraint molecular dynamics. So basically, the RNA is fixed or almost rigid, okay, by including ERMSD restraints with respect to the original. And then we complete the buffer with a salt concentration equivalent to the experimental one, adding in magnesium and sodium ions. So as I said, we have two different models, slightly different structural. And as I said, we want to do something minimalistic, but basically take a structure that you can predict for some other method and put it into order. We are going to call these two models Model 1 and Model 2, which are simulated under two different water models, Type 3P, which is kind of a standard, at least in RNA. There are better things that are coming as well. And SPCE, which is not the best, but it's still a widely used water model in the community of simulations. And we're also going to compare what happened under this protocol of simulation, what happened with the best structure, which was provided by the organizers at the end of the challenge, simulating them under water under the same protocols. And we are going to restrain one in the best case. We're going to call it best. And we're going to simulate another one, which is unrestrained, which of course it's going to suffer heavy structural modifications. So the idea of this is, or at least of this presentation, because we already did our calculation and our simulation following this protocol, is to see really what can happen once you run under different water models with structural differences. And also we're going to make a brief analysis of what happens with the thickness of the water layer that surrounds the molecule. Okay, so the idea is that at least we have a ground to play a bit and to learn a bit also which of these factors is more important for the agreement with the electronic density map. So as I said, AlphaFold makes a good job. I wanted to put this in hyphens. Okay, good, because of course it predicts something that already knows. Although the best structure compared with the target one, or the best one, had an RMSD of 4.4, which is still something reasonable. Although there are slight differences in the orientation of certain stems and another structural strand, which is the first 10 nucleotides. Okay, so this gives that the AlphaFold structure is slightly less compact, but only by 10 nucleotides, which are predicted as a single helix, I would say. But in practice, in the experimental structure, they are forming some non-canonical pairs and stabilizing and pointing inwards. So taking this into account, we see that the two models that we have actually differ in this part. So at least we have something to play that has a slightly different structure, this set. But this protrusion actually incorporates more water molecules whenever we take the water shell. So it could be also important, and we would like to know how important that could be. So for seeing the structure of the water around, as I said, I'm not going to focus on magnesium ions because we are using the magnesium ions predicted by AlphaFold. We look at the minimum distance density function, so basically the distribution of the distance of water molecules with the minimum distance that they have from the solute. Okay, so if we take the model 1, model 2, and for example the best using the deep 3-free water model, we see that there is practically no change. Okay, so the structure, we could say roughly that is basically the same around it. But if we try, for example, our best model with the model 1 and model 1 also with different water models, we see that there are structural differences that can be appreciated in a better way. Okay, so SPC and T3P, and eventually, if one has something like really sensitive density difference, that could be also attributed to the water model. Although, if we can see that both solvation shells are well contained below the 5 angstrom cutoff. Okay, so in case that we want to play with the thickness as well, we could have maybe some minor differences, but at least with the 5 angstrom, which was the number required in the challenge, that should not play any difference or any role. And also, well, here at least you can see part of the plot. I'm sorry about that. You can see that well, this is the unrestrained model. Okay, the orange one, and the blue one is the restrained model, both of the best structure provided. And you also can see that in this density function, not only you see the structure of water around the molecule, but if the molecule changes its conformation heavily, but in this case where they differ of at least 10 angstrom of RMSD, you can see that there is a substantial difference as well here. So what happens here? Okay, this is a bit noisy, but still it gives us an idea of what is the correlation generated by Chimera, which is not the best way of calculating the correlation between the density functions, but it's something that is more or less a standard, so it's also a good way to calculate differences between systems simulated or constructed under different parameters. So we selected 50 frames and calculated the correlation after an optimal alignment with the best structure that we had. So we helped Chimera to make the local alignment properly by previously aligning it with the best or the target structure, basically. So that's the best we could do. And we see that, in fact, for model 1, which is here, and model 2, there are very, very small differences of what could be the correlation, which tells us that they are somehow consistent on the different water models. Okay. But if we take the best structure and our model 1 and the unrestrained one, which is a complete mess, we can see that there is some difference that is substantial. Okay, so in my opinion, okay, I don't want to put somebody to this, but in my opinion, what I think is that not only the structure could play a role here, but also the way that we have to align the structures using the best structure for alignment could play a role there. Okay, so this could be maybe some systematic effect from the way that we have to calculate the correlation there. So in that case, it's also better to take more seriously the results that could come from the simulation of a single system or the very same structure for them. And in this case, well, you can see that if we follow the same procedure and we play around with the thickness of water or the layer that we can include there, you see that without any water considered or solvent molecule, you see that this blue line, it tells you immediately that the correlation decreases. Okay, it's less than 10%, but still is something that could be at least detected, or maybe could be more meaningful or useful to know when you're dealing with some specific regions of the molecule. Then after 3 angstroms of thickness, more or less all the curves are kind of well collapsed or converge. And here also you can see that there is a kind of apparently a big mess. But of course, if you don't take into consideration the water layer, of course, you will end with something that is way below the other conformations. Still, the difference is smaller, okay? But this tells us that basically we cannot improve substantially our agreement with experimental data if we are just playing around with the thickness of the water shell. So what I wanted to pose as a conclusion, maybe some more questions Okay, it's not necessarily that something went well or bad, but at least it could be enough to make minimalistic simulations very quick in the case that you have magnesiums fixed, or at least you know a place where they could be, and just let the water relax around. At least it could help you to elucidate if you are doing the right things, or maybe if you some particular regions you can do something. You're doing you're going the right way. Okay. Now, what happens, and this is I didn't put it before, is that we did a simulation also correcting this position of this strand, and we also obtain a marginally increase in the agreement for the correlation. Okay. So it seems that the unstructured strands and the alignment, well, the unstructured is not that important, but the alignment could be important. So that means that there must be some, or we should use, or maybe I recommend people to use something more sophisticated than Chimera and FitMap for calculating the agreement between the electronic density maps and the structure and the one generated by the structure. Okay. And also, we didn't pay too much attention to this, but the position to the ions has to be analyzed, especially if we would like to cross-check and to see if some relevant magnesiums are being well predicted by AlphaFold, which is also a possibility, and it's also so that people could be doing in this moment in other part of the world. Okay, and well, this is something that probably most of us already knew, but the thickness above 3 angstroms is plausible for obtaining reliable results or more or less converged results. I wanted to thank my people from
the team. I have a question.